So welcome to problem 3.7, which is very much like problem 3.6. The only difference is that here we are looking at another mortality law instead, the Gompertz-Makeham mortality law. So just before we get started, we can spend a little bit of time taking a look at this intensity function that we're presented with, namely mu of t is equal to alpha plus beta e to the gamma t, where we assume that alpha and beta are greater than 0 and also that we consider t to be non-negative. So why are alpha and beta greater than 0? Well, intensity functions must be positive or at least non-negative by definition. So that is why we ask alpha and beta to be greater than 0. Actually, we don't need alpha to be greater than 0 or beta to be greater than 0 as long as we don't need them both to be greater than 0 as long as only one of them is greater than 0, then we're actually safe. But the thing is, if one of them is equal to 0, then one of these terms will vanish, right? And then it's no longer called the Gompertz-Makeham mortality law. Essentially because this mortality law has a Gompertz part and a Makeham part. So the alpha is dedicated to Makeham, and his name when he lived was William Makeham, and the beta part with the gammas is courtesy of Benjamin Gompertz. And actually, if you Google Benjamin Gompertz, there is a very charming portrait of him online. William Makeham has no portrait, unfortunately, but they both contributed to parts of the Gompertz-Makeham mortality intensity. And what is the interpretation of these two parts? Well, you can see that no matter what t is, alpha will remain the same. So this is the age-independent part of the intensity. And what can that stand for? Well, that can stand for things such as accidents, natural catastrophes, so factors contributing to mortality that has nothing to do with age. On the other hand, here we have the age-dependent part, where we can see that as t changes, this thing will either increase or decrease depending on the value of gamma. And that's stuff such as, more death due to, for example, age-related illness or death due to just age in general. So the Gompertz-Makeham mortality law has two aspects, which is also why it's quite popular, because the interpretation is very, very intuitive. Now let's take a look at the goals of this exercise. The first thing we want to do is find the survival function, where we just recall that the survival function is the probability that the lifetime of a newborn is greater than the value t. And the second thing we want to do is to show that the intensity increases as t increases if we have a value of gamma that is positive. And that's not too hard because we can almost already see it in the expression. And in 3, we want to find TPX, which is the conditional probability of survival for an X-year-old past the next t years. So this is the conditional probability of survival for an X-year-old. So given that the lifetime is greater than X, then the probability that it will be greater than t plus x. Okay, now we can just write up a few definitions, so we're all ready to go. In chapter 3, we are provided with two expressions that tell us how we can find the survival function and the conditional survival functions by means of the mortality intensity. somewhere on page 25, we see that the survival function is given as the exponential to the minus integral from 0 to t of the mortality rate. And the conditional survival function, well, it is just the probability of survival past t plus x given survival past x. So if we already know the unconditional survival function, then it's actually just the ratio of the survival function t plus x over the survival function in x. However, if we don't know the exact expressions for this yet, then we can also just calculate tpx directly as e to the minus integral from 0 to t of mu of x plus s ds. Oops. Sorry. Okay. So these are the two formulas that we're going to use in this exercise.